Okay, here we are doing page 13 of properties of curves. I actually just recorded this video and then I found out there was a problem with my microphone. So that's why everything is already written down. But let me go through this with everything written down. This will be a little bit different than usual. First of all, it tells us that it wants to do a graph of this red function and this blue function, right? So we got e to the x minus 3, we got 3 minus 5e to the negative x for this interval, okay? Now, what do we know about graphing and helping the graphing process by taking derivatives? Well, if we know the first and the second derivative, we can kind of figure out what shape the graph is going to be. So let's do that. So the red function, if we take the first derivative, we're going to get e to the x, right? Derivative of e to the x, e to the x, derivative of negative 3 is 0, right? If we take the second derivative, we're also going to get e to the x, right? For the green function, if we take the first derivative, we're going to get 3, the derivative of 3 is 0. The derivative of negative 5e to the negative x, we're going to get negative 5e to the negative x, chain rule negative 1. So the negative 1 times negative 5 gives us a positive 5e to the negative x. And if we take one more derivative, the second derivative, we would get a 5e to the negative x times negative 1. So the negative 1 times 5 would be a negative 5. So how can these derivatives help us figure out what the red and the blue function look like? Well, for the red function, for example, if we made sign diagrams for the first and the second derivative, they would be very boring sign diagrams because the first derivative is constantly positive and the second derivative is also constantly positive. What kind of function has a constantly positive first derivative and a constantly positive second derivative? Well, it would be a function which goes up and is concave up. So it kind of looks like that. Hey, what do you know? It's an exponential function, right? What about a function that is constantly positive first derivative, but constantly negative second derivative? Because e to the negative x and e to the x always have to be positive. They're always above y equals 0, right? So what makes the thing positive or negative is the coefficient. In the case of the blue function, the first derivative is constantly positive, and the second derivative is constantly negative, meaning it's increasing, but it's concave down. So the second function, the blue function, is going to look like that, increasing, but concave down. Okay, now we're going to do more traditional graphing math. And then we'll see that our estimates for the red and the blue function are similar, okay? So the first thing we're going to do is we're going to find the x and the y intercepts of the functions, okay? So to find the y-intercept, remember that we want to make the x equal 0, and to find the x-intercept, we make the y equal to 0. So for the y-intercept, we're going to put 0 in for e to the x minus 3. We're going to put it in for x, so we'll get e to the 0 minus 3. E to the 0 is 1, of course, so 1 minus 3 equals negative 2. So that is our y-intercept for the red function. What is the y-intercept for the blue function? Again, we're going to put 0 in for x, so it would be 3 minus 5e to the 0, which is 3 minus 5 equals negative 2. Oh, what do you know? They both have a y-intercept of negative 2. Interesting. Okay, now to find the x-intercept, what we're going to do is we're going to put 0 in for the y. So 0 equals e to the x minus 3, and then we're going to solve for the x. How do we do that? We're going to isolate the e to the x. We're going to add 3 to both sides. We get e to the x equals 3. To get the x now, we need to take the natural log of both sides, so x equals natural log of 3. What is natural log of 3? It's about, I think like 1 point something, okay? That's the x-intercept, slightly more than 1 because the natural log of 2.7 would be 1, right? What about the x-intercept for the blue function? So we put 0 equals 3 minus 5e to the negative x. We put 0 in for y, right? Then we want to isolate the e to the negative x, so we put the negative 5e to the negative x on the other side, and so we have 3 equals 5e to the negative x. Then we want to further isolate e to the negative x, so we divide both sides by 5, so we get 3/5 equals e to the negative x. The e to the negative x, we can make it e to the positive x by inverting the 5 and the 3. Okay, so like we'll have 5/3 equals e to the x instead. Remember, the negative exponent just makes us invert things. Now, to find the value for x in this case, we just need to take the natural log of both sides. So x is equal to the natural log of 5/3. Okay, so the x-intercept of the blue function is natural log of 5/3. Next thing they want us to find the points of the intersection. So here I did that in pink. So the first step is I'm going to take the blue and the red function and I'm going to set them equal to each other, just like you did in 8th grade. So I set them equal to each other. I'm going to solve for x. First thing I'm going to do is I'm going to move everything to the left side, and the right side is going to be 0. Okay, so e to the x is here. Negative 5e to the negative x, I add it to both sides, it ends up here. The minus 3 from the red is here, and the positive 3 on the right side, we subtract 3 from both sides, and then it ends up with 2 negative 3's on the left side, which combine to become negative 6, right? Okay, now we don't like the fact that there is this e to the negative x here because it's x in the denominator, and in order to solve for x, it's nice to have x, all of the x's in the numerator. So how do we get e to the negative x out of here? We need to multiply by its reciprocal, which would be e to the x. So we multiply the entire left side by e to the x. So we get e to the x times e to the x squared. 5e to the negative x times e to the x would be just 5. And then the e to the negative x and e to the x cancel and give us a 1. And then negative 6 times e to the x. Now I have what looks kind of like a quadratic, if you remember these problems from like chapter 3. If we replace all the e to the x's with a t, then we'll end up with t squared plus 5 minus 6t equals 0. Now this is a quadratic. If I switch the negative 6t and the 5 so that I make it into descending power order, it's a little easier to factor. When I factor it, I'm going to factor it into t minus 5 and t minus 1. So t is equal to 5 or t equals equal to 1, right? And then I bring back the e to the x that I replaced with t, and so now I have e to the x equals 1, which means x equals 0 in that case, and e to the x equals 5, which x equals natural log of 5 in that case. So the two x coordinates which cause intersections are x equals 0 and x equals natural log of 5. X equals natural log of 5 is like 1.6, I found out. If I want to know the intersection point, I would put I already know the intersection point at x equals 0, right? Because it's the y-intercept, which we knew is negative 2, right? But what is the y value for the x value of natural log of 5? So I put natural log of 5 back into either function. I choose this one, okay? So e to the natural log of 5 minus 3 is going to give me 5 minus 3 is equal to 2. So my second intersection is natural log of 5 comma 2. With my calculator, I found out that natural log of 5 is actually around 1.6. So now it tells me to graph the functions. And remember, the red function is going to look kind of like this. The blue function is going to kind of look like this. The red function first, I'm going to... we haven't talked about asymptotes yet. I kind of skipped that, didn't I? For B, it says, discuss the asymptotes, the horizontal asymptotes of f and g, okay? So in the case of f, the red function, if I put negative infinity into e to the x minus 3, e to the negative infinity is a very small number. So a very small number, basically 0 minus 3, gives me a horizontal asymptote of negative 3. If I put in a very big number, positive infinity here, this would be infinity minus 3, which is basically infinity. So if I go far to the right, it just gets big. Okay, what about the blue function? For the blue function, it's a little bit the opposite. If I put negative infinity in the blue function, then the second term, negative infinity, is taken the negative of, so this ends up being a huge negative number. Okay, huge negative number. If I put in a big positive infinity, then I'm going to get 3 minus 5 e to the negative infinity. And so that would be a super small number. And so this would be 3 minus 0. So if I go far to the right, my value of the asymptote is going to be 3. So the blue function has a horizontal asymptote at 3 on the right side. The red function has a horizontal asymptote of -3 on the left side. So here when I'm drawing the graph, it tells me to draw a graph in D. I'm going to draw a horizontal asymptote for the red function at -3. And I'm going to draw a horizontal asymptote at +3 for the blue function. And I have my two intersection points. One of the intersection points is the y-intercept, which is -2. Both of them go through 0, -2. And then, of course, I have my second intersection point, which is 1.6, 2. And so 1.6, 2 is about here. And so I draw my blue function with this shape, hugging the blue asymptote, but going through both of these points. And the red function with approximately this shape, it's going to go through the 2 points and hug the red asymptote. Okay, so that's how we can use the first and second derivative to know the approximate shapes, and then we have all of our usual techniques to help draw details like intersection points, y-intercept, x-intercept. I didn't really use the x-intercepts here because I didn't really need to, but I'm sure that if we went ahead and put them in the calculator, we'd see that they're approximately in the right place. Okay? All right, let's go down to the next problem, number 7. So number 7, again, we're going to use traditional techniques and calculus to try to draw a graph of natural log of 2x minus 1, parentheses, minus 3. By the way, we have already drawn graphs like this using transformations, right? But this time we're going to use traditional techniques. So first thing we're going to do is we're going to find the x-intercepts. Remember, to find x-intercepts, you need to make the y value 0. So if I put 0 here instead of f of x, that would help me find the x-intercept. So 0 equals natural log of 2x minus 1 minus 3. I'm going to isolate the natural log. So I add 3 to both sides, and now I have the natural log equal to 3. How do I get rid of the natural log? I do e to the 3 and e to the natural log. The e to the natural log cancels out, and I end up with e cubed equals 2x minus 1. Now I want to isolate the x, so I add 1 to both sides. So I have e cubed plus 1 equals 2x. Now I want to isolate the x, so I divide both sides by 2, and I get e cubed plus 1 divided by 2. In my calculator, I found out that that's 10.5 about. Okay, so that was the x-intercept. Then it says, can f of 0 be found? F of 0 is when you put x equals 0 into the function. Remember, that corresponds to the y-intercept. If I put 0 into this function, notice that I'll get 2 times 0 minus 1, so I'll get natural log of -1. Can I do natural log of -1? No, natural log of -1 doesn't exist. So what does that mean? It means that there is no y-intercept. Okay, what about C? Find the gradient of the tangent to the curve at x equals 1. Okay, now they want us to take the derivative because gradient of the tangent is the same thing as the derivative function. So let's find the derivative of this function. So natural log of something minus 3. Natural log of something, the derivative would be 1 over something. And then we do the chain rule. Chain rule of 2x minus 1 would be 2 in the numerator. So this is our derivative. Then they want the derivative at x equals 1, so we're going to plug in x equals 1, which is 2 over 2 times 1 minus 1, which is 2 over 1, which is 2. So the derivative at x equals 1 happens to be slope 2. Okay. D, find the domain of f. So we know that the domain of the natural log function is x is greater than 0, right? X is greater than or equal to 0, or x is greater than 0? X is greater than 0 because, remember, there's an asymptote at x equals 0 for natural log. Okay, what about natural log of 2x minus 1 minus 3? Where does the asymptote end up here? Well, one of the ways we could find the new asymptote is with transformations, right? So if the original asymptote is x equals 0, let's do these 3 transformations on the asymptote and see where it ends up. Well, remember, the -3 on the outside of the parentheses is a vertical translation. Does the vertical translation affect the vertical asymptote? No, it doesn't. So we can ignore the -3 here. We'll just look at the 2x and the -1. Which one comes first, the 2x or the -1? Remember, inside the parentheses be Zaha world, so it's opposite of PEMDAS order. So the first thing that's going to happen is to subtract 1, and then we're going to do the 2x. What does subtract 1 in the parentheses do? Remember, it moves it to the right by 1. So the asymptote was at x equals 0. First step is we're going to move it to the right by 1, so now the asymptote's at x equals 1. Then we are going to do the 2x, which is a horizontal compression by 2. Remember? So 2x makes it look like it's going to get bigger, but it's actually going to get smaller because it's Zaha world. So instead of being at x equals 1, it's going to be half the distance from the y-axis. Instead of x equals 1, it's going to be x equals 1/2. And that is where our asymptote's going to be. Another way you could do it is you could say, okay, I know that the asymptote's going to be at the position where the inside of natural log is 0. And so you could set 2x minus 1 equal to 0, and then you would solve it, and you'd find out that it's x equals 1/2 also. If the asymptote is x equals 1/2, that means that the domain of this function is x is greater than 1/2. Okay, so that is the domain of f. Then it says to find the second derivative of f and explain why f is concave down for all x. So finding the second derivative of f means we take the first derivative, which is 2 over 2x minus 1, and we're going to do the derivative of that. I'm just going to rewrite 2 over 2x minus 1 first as 2 times parentheses 2x minus 1 to the negative 1, because this is the same thing as 2 over 2x minus 1, but it's easier to take the derivative because it looks like chain rule. Okay, so to do this, we're going to write the coefficient first, 2, and then we're going to take the exponent negative 1, we're going to write it to the left of the inside of the parentheses. We're going to write the inside of the parentheses exactly as is. We're not going to take the derivative yet. And then we reduce the exponent from negative 1 to negative 2. Finally, we're going to do the chain rule on the inside, so we multiply it by 2 at the end. Now we have 2, negative 1, and 2, which can all be combined to negative 4. And then in the bottom of the fraction, we're going to put the 2x minus 1 squared, right? Because there's a negative exponent, we can put that in the bottom. It makes it a little easier to understand what happens with this second derivative depending on the value of x. Now remember, what are the possible values of x that we can put in there? Anything bigger than 1/2. Can we put 1/2? No, it has to be bigger than 1/2. So if we look at this, if we put in any number in this denominator, negative or positive, notice that the whole thing becomes positive because whatever you put in here and square it is going to become positive, right? So basically, the top is negative, the bottom is always positive. So this second derivative function is always less than or equal to 0, right? When is it 0? When we put 1/2 in here. Ooh, but when we put 1/2 in here, it becomes perfectly 0. Okay, in the denominator, but we can't because remember, x has to be greater than 1/2. Okay, can this thing ever be 0? No, it can't, because then the numerator is never 0, so this thing can never be 0. Okay, so it's not less than or equal to 0, it is simply less than 0. Okay, so it's always second derivative negative, which means it's always concave down. Okay, so that's our explanation. It's for this domain of x is greater than 0, it's always concave down. Okay, let's go to the last one. It says graph the function showing the features you have just found. Okay, first of all, we're going to put a asymptote at x equals 1/2. We're going to put an x-intercept at approximately 10.5. And then it's going to be concave down always. And it's going to be, what else do we know? We know that the gradient of the tangent at x equals 1 is about 2. It's about like that. Or it's about like that. Okay. So, log shape. Did we use all the information? No y-intercept. We use the x-intercept. We use the slope. We use the domain. We said it's concave down all the time. Okay, so we did everything. We already kind of knew what log shape was anyway. All right?